I want to do something unique today in the sense that when I teach a lot of people programming, because especially when I did tutoring at ASU, a lot of them, when they learn a new concept and we go through a couple examples, they get why it's used and kind of like why we have that concept, but sometimes they don't know when should I or when will I spot that, I need a for loop here, or a while loop here, or I just know I need a loop, but which one should I use? Well, sometimes the answer isn't easy. Sometimes that's one of the things I really like about programming, is that you can solve the problem a lot of different ways, and sometimes it's hard to view a right answer amongst the different solutions, which makes it kind of fun to see what everyone comes up with. And sometimes you can, like I once was tutoring somebody for a homework solution for a problem where you had to make a rock, paper, scissors game. And he did it in 380 lines of code, using no loops whatsoever. And because he didn't understand while loops, or for loops for that matter. And so I walked it through with him, and so afterwards we were able to shrink it down to I think like 25 lines, and the game could run for as long as you wanted to. His only ran 3 times, and then said the winner. So it was like a best out of 3. The new one, you just put in the number of games you want to be best out of, and it'll run, and it's 30 lines of code. No matter what you want to do, it'll keep working. It's expandable, but it's only 30 lines versus a 380 line code that can't expand. So there's sometimes you can spot a righter answer, like a more correct answer. I don't know if right is the right word. So what I want to do today is I'm at Project Euler, which is a really fun place to practice your programming skills. What they do is they have an archive of problems. I'm logged in. You can see which ones I've solved and such. Let's see, I haven't solved many more. Oh, yeah, I think up to 20 I solved. They have math problems that you can't brute force by hand, that you have to solve using programming. And it's pretty popular. You can see like 600, but you can see how many have solved by it. And you see 600,000 people have solved the first one, so that's a fair bit of people. But as you go down, you see, whoa, way less people. And in fact, if you go, there's some that I think like 80 people have solved. You can only see how other people solved it until you've solved it yourself. So you can look and see other people's answers. So it's a good idea of when to use certain, different thinking processes you could use to solve the same problem. And maybe right now in this case, 2 solutions aren't any better than one or the other. And maybe if you're doing a certain application, you might want to do it one way because it's easier to integrate it with another part of the code. Right? I've run into that a lot of times where I'm doing it the way I normally do it, even though I'm aware of another solution, and then I run in, I have to integrate another piece of code that would work better with the other way. So it's good to keep your mind open to all the different solutions, right? If someone solves another way, don't get in a whole flame war, which is, you see a lot of them in programming. But just because you guys have different solutions does not mean a flame war should entail. So you'll see in their About page, they have a statement that I agree with. I learned so much by solving problem XXX, so it's okay to publish my solution elsewhere. They say that they don't strictly say they'll come after you if you post them down, right? They encourage you not to because of that epiphany moment of solving them. And I know I've had plenty. I've gotten in groups of people, and we've been working on it together, and we go our separate ways, and we come together and see how we solved it. And there are just some moments where you're dancing around based on how you solved it. I mean, some of those where you have like a matrix, and it's like find the biggest product around them. Oh man. Those were blasts. Those were fun. So what I wanted to do is I didn't want to go through solving a bunch of them for you. Okay, the first 3 or 4 or 5 are pretty simple. I'm sure you get them after a couple minutes. And I wanted to solve a couple first in Python, and then I was going to do another video on C just to show you because they're not that simple. I hope I'm not taking away a ton of your. Oh yeah, I'm just going to solve the first couple as an exercise of because I solved them like 2 years ago, I think. It's been a while, so this will be it's almost like I don't remember what the problems were. I'll be like I'm looking at them fresh, and I'm going to go through my thought process as a programmer of what I should use or what solution I'm going to use. And there's probably, I'm 100% sure there's more efficient solutions, okay? But we'll look through and we'll see kind of how I go about it. So let's start with the first one, okay? Let's pull up Python, all right. So let's first read it. Okay, if we list all the natural numbers below 10 that are multiples of 3 and 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Find the sum of all the multiples of 3 or 5 below 1,000. Okay, alright. So we obviously can't brute force this with hand, okay? This is the simplest problem on the site, and we already just can't BS it by hand. There's one I know on there later on you could have, but it kind of defeated the purpose if you did it that way. So let's look at some key things. Okay, so we're going to have to take the sum of a group of numbers. Okay, so what I'm thinking right now is that a list right here. We're listing all the natural numbers. Okay, I'm thinking an array or a list, right? Okay, so I'm thinking we can store all the multiples of 3 and 5 below 1,000, and we can put them in a list, and then we can sum that list. Okay, that's what I'm thinking of now. Okay, so to keep track of them, I'm just going to put them all in one place, one little package, one list, because in Python we don't need to specify size. C, it'll be a little bit more tricky here. And I'll just sum them. So how am I going to go about finding the multiples of 3 and 5? Well, we have that useful operator. Let me bring up a shell. I have the useful operator modulo. If I go 5 modulo 5, it returns the remainder, right? So 5 is obviously divisible by 5, so there's a 0. So you notice if the remainder is 0, if I go 2, it means it's divisible by that number, right? So if I wanted to test if something's a multiple of, say, 5 and 3, I could go 5 modulo, or let's just pick a number. Let's pick 12, okay? Which we know is not divisible by 5, but is divisible by 3. So I can say, equals 0. And 12 modulo 3 is equal to 0. Whoops. We get false, right? Because obviously it's not divisible by 5. If I just do 12 divisible by 3 equals 0, I get a true, right? So because we know it's divisible by 3. So, okay, so I should test every number up until 1,000. This seems like a base solution that you can improve upon if you want. But I think I'll test every number up to 1,000 and just check that 12 modulo 5 equals 0 or the number modulo 5 equals 0 and the number modulo 3 equals 0. Okay, alright, okay. So how should I loop through those numbers? Well, I think I just said the answer there, loop, but how should I go through all those numbers? Well, if I want to go through a bunch of numbers over and over and over and over and over again, well, if I normally wanted to test the numbers 1 to 1,000, or, we can start at 6 at this point, and I'll show you why in a second, because I'm thinking about it. See, thinking ahead of time. This stuff comes natural. Normally, if I want to test those numbers just outright, I would need to, write that test line for 6, and then 7, then 8, then 9, then 10, all the way to 1,000. I need 1,000 lines of code just to test all of them. No, I'm not doing that. But you notice each line is going to be similar, right? It's going to be some number x modulo 5 equals 0, and some number, I don't know, maybe, same number, modulo 3 equals 0, right? It's a similar thing. So whenever you have to repeat a part of a code over and over and over and over again, instead of typing it out over and over and over again, you want to think one of two things. I want to think function or loop, okay? In this case, we could do either, because if I made a loop, I could have it just go, and if we're thinking loops real fast, this on the side, we got to think either for or while loops, all right? While loops are usually if we don't know how long we're going to run for, and sometimes if you don't know how your counter will change a bunch of different ways, which isn't always true. You can sometimes use for loops for that. But if we don't know how long we're going to run for, you usually want to use while loops, because you're saying while some condition is met. I may not necessarily know when that condition will be broken, but I know I want to stop when it is. So I know how long I want to run for, and I know I'm going to be incrementing in 1, which, you kind of, for loops were made after while loops, I'm assuming, because a bunch of people were using while loops and incrementing by 1, and they're like, dude, screw it, let's just make a for loop. But if you're ever incrementing by a set pattern every time, and you know how long you want to run for, that's a good trigger for a for loop. Now, if you're incrementing a bunch of times and don't know how long you want to run for them, that's probably a while loop. But there's some times you want to intermix. But this is the general case, right? So I know how long I want to run for. I want to run up until, let's say, 999, really. Or just basically our counter is, as long as it's less than 1,000, of course, because it says below, yeah, below 10, so below 1,000. And I'm going to go up by 1 every time. Okay. There's probably a way that you could update it every time to go up better instead of testing every number. You may be, I don't know, but we're just going to do a base solution here. So, all right. So let's do that. Okay, so I'm going to make a list. I'm just going to call it nums. Just call it that. And let's just stick in 3 and 5, because obviously, if we get list all the natural numbers below 10 that are multiples of 3, 3 or 5. Look at that. That changes a lot. Because I remember 3 and 5 were in here, which is not good. So 3 or 5. Okay, that changes things a bit. So now, if we had that same line where it was like 12 modulo 5 equals 0, or 12 modulo 3 equals 0. All right, now this would be true, okay, because 3 goes into 12. All right, so I'm going to start it off like this. Okay. I'm just going to start with 3 and 5 because they're obviously multiples of themselves. So I'm just going to stick it in there. I'm going to start at 6. Okay. So I'm going to say 4x in range, okay, 6,000. So I'm going to start at 6 because nothing below 3 and 5 is a multiple of 3 or 5. And 3 and 5 in that kind of range are like 4, that's not a multiple of 3 or 5. So from the range of 0 to 5, I've gotten all the multiples of 3 and 5 already. So I might as well start at 6, right? Might as well save us a little bit of time. So I'm going to go at 6, remember, because this is inclusive, this portion right here, to whatever this number is minus 1, so 999, right, because we want below 1,000. I'm going to say if x modulo 3 equals 0, or x modulo 5 equals 0, okay, I will append it. I'll just stick, it's obviously, if one of these statements is true, it's a factor. So I'm going to stick it on to nums. Nums append x. Pretty simple. So what's it going to do? Well, it's going to go from 6 to 1,000, and it's going to, this code already is going to find us all the multiples of 3 or 5. Python. It's beautiful. So what are we going to do now? Well, there's a nice little word called sum that takes an array and gives you the sum of it. Well, okay. Well, then I might as well just go print, if I can type, sum nums. We're going to take the sum of nums. Sum nums. Ah, man, I didn't plan for that. I swear, pun not intended. Yeah. And I have the answer because I've already solved this one. Okay. I'm just going to call it Euler. And we see 233,168. 233,168. So we solved it. Boom, done. But say I want to make this code adaptable, because maybe a client's like, I need this code to work if I want to plug in any number, right? Like, so say they want to find all the factors of 3 and 5 below 100, or below 999, or 2,659,000,000. Well, if you want to run over a piece of code over and over and over again, but you want to put in a different kind of value every time, you want to make it adaptable, function right there, keyword function. So what I'm going to do is I'm going to say def sum factors. I'm going to call it sum factors 3, 5. Okay, and you're going to put in the limit, all right, the number that you're going to go to. Okay, I'm going to copy this. I'm going to head on down. I'm going to paste it in there, and then I need to obviously reformat everything. Alright, so we have our function, right? But instead of 1,000 here, I'm going to do limit. Because it's going to start at 6, because no matter what number they put in, alright, and we can even put something here. If limit is less than 5, say that, or less than 6, you know, we could say, we'll do a little side one. 4x in range 0 to limit. Nums, we got to reset nums then. I'm going to keep that, I don't want to confuse you guys. So sorry, I gotta say what I'm thinking. So I'm saying if the limit's less than 6, we don't know where it is less than 6. Could be 0, could be 1, could be whatever. I'm just going to say, I'm going to make nums a blank list real fast, because we don't know if 3 or 5 are in it now, right? We don't know. Because what if they put in 4? Then 5 shouldn't be in there. So I'm just going to say nums for x in range 0 to limit if x modulo, it's basically the same line of code right here. Okay? Nums.append x. And whatever we do at the end of the day, okay, I'm just going to put an else here. Whatever we do at the end of the day, we're just going to return the sum of nums, okay? So instead of print, I'm going to do return, okay? Pretty simple. And here's our function. So now, if our client's like, hey, I need this to work for any number I put in, well, there you go, buddy. Okay. So this is a really basic solution. You know, if you're a beginner coder and you want to think about the mindset of a programmer, this is a really good place to start. Okay, this is how we go through it. Now, there's some, you know, better solutions I could do. Like I could do factors. I'll just do it like this. I'll say nums is equal to x modulo, and I'll explain what I'm doing in a second. Or x modulo 5 equals 0 for x in range. Whoops. I'll just do 0. And then print. So there are obviously improvements you can do, right? And this is one. This, if I put these brackets right here, I say I'm making a list, right? But what am I putting in this list? Well, I have an expression. So it's like, whoa, buddy. You didn't put in numbers like this guy. You put in an expression. But I think I get what you mean. He's saying, okay, I'm going to evaluate this expression for whatever you tell me. And whatever satisfies it, I'm going to make a list out of it. Okay? So pretty straightforward there, but you can see this is a lot less code for that, right? And if I put this inside of a function, like the function up above, all I need to do is a little limit like that, okay? A two-liner, basically, right? So there's always, so it's one thing to write a piece of code that works, okay? And programmers know this. It's one thing to write a code that works. It's another thing to optimize that code, okay? There are entire there are entire subsections of programmers that spend their entire lives optimizing like single problems, okay? Optimization is huge, okay? Especially as we approach Moore's Law, you know, Moore's Law is a law saying how much faster computers are going to get, you know, basically means how many transistors, which are like the essence of how computers work, how many transistors we can fit in a computer is going to double however so often. Sometimes they change it from a year or 2 years to like 16 months, you know. Sorry for getting the numbers wrong. But, you know, some say the law isn't going to hold for very much longer. And that's why quantum computing is coming up. And not only that, it's because quantum computing is going to go like 1 billion times faster. It's like 300 million times faster? I forget the exact number. You can look it up. It's pretty awesome. But efficiency is key as our computers may reaching a physical limit on how fast our computers are going to go. And optimizing what's already there is going to be really important. You know, and plus, if you have a lot of programs running at once, computers even nowadays only have so much RAM. If you want to run a ton of things, you're going to want to optimize those things so that you can run more and more and more. I'm sure if you're running a giant game on ultra graphics, your computer slows down, right? Because it's not optimized. If you run on the worst blocky graphics, you know, like maybe Minecraft, for instance, and you make your render distance really short, your computer runs a lot faster because it's optimized in the sense that it does only what it needs to, and that need is made smaller, right? Here we had to do an if statement, we had to reset an array, we initialized array, we have 2 separate for loops. We don't go through both of them, but we're appending to a list, and we're doing all this stuff. Here, we just got one little task. We just got to go through 1,000, we got to find everyone in here. That satisfies the expression. Okay, let me just make sure that works real fast. Sometimes I have trouble doing my little 467. Oh, x equals 5 equals 0. Gave me a little error there. Let me see if that works. Whoa. Alright. I obviously have a little error. Let me come back and fix that real fast. Be right back. Alright, so I found the error. It was the way I had it. It was putting in true or false into the array, and so it was summing all the trues, which is just one every time. So I should have done x for x in range 0 to 1,000 if x modulo 3 equals 0 or x modulo 5 equals 0. So this is how you do it. Took me like 5 seconds. I was like, oh, I gotta have the conditional at the back. So my bad. Okay, and if we run that, I'm just going to take out nums. So it was telling us the previous one how many factors we had, which was 463. We get the right answer. Okay, so this is a one-line improvement. So let's move on to the second problem. Okay, probably work out the first three. Even Fibonacci numbers. Okay. Each new term in the Fibonacci sequence is generated by adding the previous two terms by starting with 1 and 2. The first 10 terms will be 1, 2, 3, so on. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even valued terms. Alright, so let's break it down. So we want even numbers. Okay. That means to me that we're going to use modulo 2 a lot. Okay? No, modulo 2 like that. 2 modulo 2, 0. That's our test for even, right? If it's divisible by 2. Okay. So we're going through the Fibonacci sequence. So that says to me a loop. We want to do a sum, find the sum of all the even value terms. That means we'll probably want a list. Okay. And then we can use that sum function like we did before. Okay. And we don't necessarily know, at least I don't, I don't know if you do, know when particularly the Fibonacci sequence will exceed 4 million. So I don't know how long it's going to run for. I know I want to loop through something. Okay, that says to me a while loop that will just keep track of Fibonacci sequence for. 10 terms would be, okay. Alright, let's get started. So they want us to start with 1 and 2. Okay, because some people start the Fibonacci sequence with 0 and 1. And if we did it that way, that'll give us a different sum of whether we started with 1 or 2. It'll be 1. The difference will be 1. Which is kind of not a big deal, but it's the difference between a right and wrong answer here. Okay, so let's do the Fibonacci sequence first. Okay. So, I need to keep track of the last two terms. Okay. So that means I probably need to make two variables. Okay, so I'll make x1, and they want to start with 1. We'll start with 2 here, and x2 is equal to 1. Okay, so x1, we'll make this 1 too. Alright, so the current term will be x2, right? The previous term will be x1. Okay. Alright. So I have these guys. And I'm going to say while x2 is less than 400,000, 40,000, okay, 4 million. I gotta remember how many zeros are in 4 million. 6, right? It is 6 zeros. Okay. It looks like times 2. I was like, wait, what? Alright, so as long as x2 is less than 4 million, we're going to keep working this code. Okay. So what does the Fibonacci sequence do? Okay, well, x2, the new term, is going to be equal to the sum of these two guys, right? That's how the Fibonacci sequence works. If you guys know if you don't know the Fibonacci sequence, sorry, I should have explained that. It's the current two guys, 1, 2. The next guy in the sequence is the primary, the most recent term and the second to most recent term added. So in this case, it's 2 and 1. So our new term is 3, right? So now we have 3 and 2 as our two most recent guys. So 3 plus 2 is 5. Okay. Two most recent guys are 5 and 3. 5 plus 3 is 8. Okay. And so forth. Okay? So that's what we're going to do here. So x sub 2 is equal to x2 plus x1. Now x1 is going to be the old x2, right? But if I just do this, well, hold up, I've lost what x2 was, right? Because x2 has changed. It's no longer what the most recent guy was. He's updated. That's not good. We've lost him effectively. So what we should do is have a past variable. Let's go past equals x2. Okay. So past equals x2. x2 is equal to x2 plus x1, so we update it. Then x1 is equal to the past value. In fact, I'm going to call this past x2. Past x2. Okay, so we have a Fibonacci sequence going. Perfect. Now, we want to keep track of which guys are even. Okay. If x2 modulo 2, so if he's even, if equals 0, let's append him. Let's get rid of this, by the way. I'm going to comment this out in case you guys want to keep looking at it. So if 2 modulo 2 equals 0, what are we going to do to it? Well, we need to keep track of it, so we need to append it to, like, say, a list, right? A list is what comes out into my mind. If you have another way of thinking about it, sure, go ahead. But the thing that's useful about a list is, say you have, one, how are you going to do this with just variables, right? Are you going to, I have no clue how you would ever do it by just making variables. I don't think it's possible. But if you wanted to just store each separate one in its own separate variable, well, tough luck, because you don't know how many there are, so you don't know how many variables to make. And you'd have to name, I don't know, say there's 50,000 factors. Do you really want to type out x1, x2, x3, x4, x5? No. Let's just put them all in one variable. Like last time. Why don't we just call it nums? Okay. And likewise, like the previous function, I'm seeing this, that we could put in a function, instead of 4 million, have a variable here, a parameter that the user puts in, right? So that's another way to make your code adaptable, maintainable, all these little things, right? To make it exportable, you can make libraries out of it, you can do whatever. Okay, so I need to make a list to append this to, right? I'm going to be appending x2. Okay, so I'm going to make this nums list. I'm going to say nums is equal to that. Okay. First, I'm noticing right now that, because remember, I haven't done this in years. I'm just doing this right now for the first time. Right? Okay. So I'm going through the thought process with you guys. So I see that it starts at 2 and 1, right? So 2 should be on there. 2 is an even number. Okay. But I start off by updating it, right? There's 2 ways I could fix this. I could just stick 2. And so we lose 2, right? That's what I meant by it's updated, right? We update x2, so it's no longer 2. So, okay. And then I'm seeing one problem that we could run into. And that problem is, the first time we get past 4 million, right? Say x2 is 3,500,000, right? And we add, say, 1 million to it, right? It's 4,500,000. We should break out, right? But it's not going to break out until it pops up to here again, right? But down here, say it's divisible by 2. Oh, it's going to put something bigger than 4 million on there. That's bad. So I could put if statement, say if this is true and it's less than 4 million. That's one way to solve it. And x2 is less than 4 million, whatever. Okay. I could do that. I don't feel like doing that because I already have an expression up here. I don't like putting expressions twice if I don't, if I don't have to. Okay. So what I could do is I could do something interesting. I could say, I could either put this up here, right, to solve that problem of not having 2 in there, but then we run into the same problem that, that would fix it. Okay. By the way, I'm just going to put nums right here. I could put 2 in here and do it this way, but then we run into the problem of the 4 million. Okay. So let's think about this. So if x2 is, start off, we just check 2, boom, put it in, right? Then we update it, then we check, right? Solved, okay? Because once we check if it's greater than 4 million, we're not going to reach this if statement. We're done. That solves it. Another way, you could have kept this statement down here that I'm seeing right now, I'm seeing this, if you kept it as x1. Because if x2 is bigger than 4 million, it's going to get above 4 million, and x1 is still going to be below it, and because it's, the way x1 gets to be above 4 million is going to be if x2 was greater than 4 million, and then, it updated and passes its value off, which just isn't going to happen unless it goes, it's got to get x2 above 4 million, and then go through it again, but it won't go through it again, right? Because it's going to stop when x2 is greater than 4 million. So if we just check x1, we know we'll never, because x1, if we kept it below, I'll put it down here again just for you to see what I'm talking about. If we kept this, right, x2 is updated, x1 is now past x2, so x1 would be 2, our first loop, right? Or x1 would be 2, our first loop, and then we check it. That way we don't skip over the 2, and based off what we just said, we won't get anything above 4 million. So this is a solution. And this is a solution. Now, tell me, which one would be better? I don't see any advantage to any of them, really. I see no advantage to either one. So see, there's multiple solutions. So if somebody comes up with a different solution than you right off the bat, never be afraid to say, is that better than mine or not? Don't immediately go, oh man, as a noob or something, or that may look a little bit more efficient or something. Just analyze it. Is that better than mine? If you don't really come up with an answer right off the bat, maybe it's not. At least not in a huge sense. Alright, so I see a lot of programmers, I do a different way than them, and they go, oh man, I didn't do it right. Well, what do you mean you didn't do it right? You solved the problem, right? It's like if I gave you a math problem, right? And you did 3 times 2, and somebody else did 2 times 3, well, you get the same answer, but is it any better to do 3 times 2 versus 2 times 3? No. So if your professor does 3 times 2, and you did 3 times 2, or 2 times 3, don't feel all bad because, a smart person did 3 times 2, and I did 2 times 3. The answers are the same, okay? And there's no, a lot of times there's not anything better about them, okay? Okay. Looks pretty good, and then we'll do some numbers. Then we'll print it out. Okay, so let's run through this. We get our first 2 terms in the Fibonacci sequence. We make a blank list. As long as it hasn't gone over 4 million, like the problem stated. We just check if it's even. If it is, we just pop it in the list. Update our Fibonacci term by summing the 2 terms, putting in an x2. Did I just burp? I'm sorry. x1 is the past x2. And then when we're done, we just print out the sums. Now, see, it's not... When you first look at the problem, as a beginner programmer, you're like, what am I supposed to do? It's not bad at all. In fact, you could probably pop in another one-liner. You can... Yeah, you could probably pop in another one-liner. Yeah, I'm thinking. Let me put a little test down here. You probably see. I didn't make a one-liner for this when I went through. This is how I solved it. But first, let's see if we solved it. Okay. 461. Blah blah blah. Let's get that out of the way. 461 3732. Yeah, we solved it. Nice. So let's try something real fast. I'm going to do a list like this. I'm going to say x while x is less than x is less than 10. I gotta increment it. Let me pause it real fast and see if I can think of a one-liner to show you guys, and I'll walk through my steps for that. Now, I've come to the conclusion you can't do a one-liner here. And my thought process is you can't just do one simple if statement because you need multiple variables that you're incrementing and such, and you just can't do that in one line of code for one of these declarations. It needs to be something simpler. So that would rule out a one-liner for this. So this seems like if there had to be a close to optimal solution, I'd say it's something. Okay, well, I mean, I think I'm tooting my own horn at this point, but I'd say the optimal solution isn't far smaller than this. Okay, that's what, I hope that doesn't sound egotistical, because I'm not saying this is a very genius solution. It is a solution, though, that we saw. Okay, so let's comment this out, and let's do the final problem 3, okay? Now for this, I don't want to do any more. One, because I don't want to risk the wrath of the community that I like to be a part of, Project Euler. And I don't want to ruin it for you guys, okay? There's a lot of times where, like the reason we go to school is because, you could, if you spent your life, you could probably reprove a lot of those theorems. But it took some of those guys decades of work, right? And the thing about, like, mankind, we always want to be improving. And so, sometimes you lose a little bit of the aha just so that you can bump yourself up to where the last guy left off so we can continue. So learning about a lot of these things is, important, but there also comes a time where you need to learn how to struggle and find your way through, say, a mathematical proof or problem on your own. And I think Euler is a great playground of sorts for that. You can learn any theorem you want. There's a billion different math books for any kind of style of math you want to learn. But to figure out how to, when you come at a problem that's just not your straight out of the math book, there's nothing that can straight up teach you how to solve those besides solving them yourself. So I'm going to solve these first 3 to get you maybe in a little bit of a rhythm, or see how you may approach it. I remember this one. This one's actually not a good one that we're going to solve first. We're going to do 4 first. To get in the rhythm of how you may start struggling through these, struggle gives it a negative connotation. Maybe I should say fighting your way through, battling, I like that. I always picture a problem in code as like a boss fight in a video game. I'm always taking them on. I love viewing it like that. Spoiler alert, answer, but we're going to solve it ourselves. Okay. I remember that prime one, actually. I solved like the first 12 before I solved the prime one. Because if you try to brute force that, the last one, if you read it, the prime one, if you brute force it, what was that? If you try and brute force it, it doesn't go over well. You can't brute force that one. So you have to know some things about mathematics, like the largest prime factor is can only be equal to or less than the square root of that number. And there, I just gave it away. Shit, I'm sorry. I shouldn't have cursed. But let's read this problem. It's gonna be the last problem, and then I'll probably do this playlist and see if anyone wants to see it and see. If you want, let me know if you want to see it and see as well to solve those ones. Otherwise, maybe that's a challenge. I'll leave it up to you guys. Solve it and see. That's what I'm going to do. A palindromic number reads the same both ways. The largest palindrome made from the product of 2 two-digit numbers is 9009, which equals 91 by 99. Find the largest palindrome product made from the product of 2 three-digit numbers. Okay. All right. So we're going to need to get out of here, shall? Woo! That's not what I want. I'm gonna be honest. When I solve the errors, when I pause them in a lot of my videos, I totally jam out. I have a playlist always ready for when I'm solving errors for you guys. All right. So let's get back to business. So we're going to be cycling through every 3-digit number. So what are the 3-digit numbers? 100 to 999. Okay. 100, 999. I'm going to cycle through those guys. I'm going to cycle through them. That's ringing a bell for loops. Hopefully you guys that are doubting loops are starting to see, man, maybe there's something I should rethink. I knew a guy that hated functions in programming. And he would do every assignment without ever doing functions. And his code was atrocious. And his teacher was like, oh, very smart, I see you're challenging yourself. No, he just did it because he hated functions. Which is like, you can't program without functions. Like you can't make a linear program without functions. Functions allow you to make programs that can branch off and go all over the place and redo things or do things in different ways and become efficient and do multiple things at the same time. You just can't make like imagine if you made a server that just is in a while loop and some client comes in and then it does whatever it needs to do once and finish. Like there's no way for you to jump back up or anything. Like you can't program without functions. So I don't know where he's at in his life right now, but hopefully it's in a more function-filled world. He's come to accept the necessity and not necessarily evil of functions. Sorry for the side story. All right. So we're going to product these guys. Okay. So we want to keep track of a group of numbers that are palindromes. Okay. So I'm going to make a list. I'm just going to call it nums again. Our trusty nums. It's a program you develop your own style and you'll get your default variable names. Actually, every program I met has their own default variable names. You name them after your friends, maybe your cat, like the day my cat died, every variable of that code was named Scooter, man. She was a good cat. Nums. Okay. So I'm going to say for x in range 100 to 1,000. I was 10,000. I would have got us a big number. So for x in range 10 to 1,000. Okay. Just gonna make a bunch of little spaces. Brings down a little bit. So for that, okay, so for every number from 100 to 1,000, we're gonna multiply it, unfortunately, by every other number from 100 to 1,000. That means I'm looping through something once, but also within inside of each loop, I'm looping again. That's a nested loop. Because I'm going to test 100 with every other number, and then 101 with every other number. And to get every other number, I need to go through a loop. I know when I first started, nested loops made my brain hurt, but bear with me. Biology, I made my first experience with nested loops was a triple nested loop making a dihybrid cross calculator for biology class. Maybe I'll do a little video on that. Who knows? Alright, for y in range 100 to 1,000. Alright, so I'm going to say num, getting real creative with these variable names. Real creative. Num equals x times y. Okay. Now I gotta test if it's a palindrome. Okay. So first, I'm gonna assume it is one. Optimism. Okay. And I'm gonna say, innocent until proven guilty, man. Prove to me that it is not a palindrome. Oh, well, alright. Okay. So, I have an idea. So we're going to make this a string to compare digits. So I'm going to say strnum is equal to strnum. Woo! Okay. And then I'm going to say for x in range 0 to, bear with me for a second here, I'm thinking, see, I'm just doing this on the spot too, so I'm experimenting. Alright. Word 1, STM. Let me think. Alright, here's what I'm thinking. So we're going to start the first letter, the 0 one, right? Like, for instance, let's say we have the number 4,224. That's a palindrome. So we're going to go from 0 to the length divided by 2. The length of this is 4. Okay. Divided by 2 is 2. And the range right here is non-inclusive, so it's going to go to 1, right? So 0 and 1. So I'm going to test the first guy, and I'm going to test him against the last guy. If that checks out, I'm going to go to the next guy, and I'm going to test him against the next guy. Now, what happens if I have an odd number? Well, let's think, before we do that, let's think of how our code would handle it. Okay? Say I have 3, and it's going to, I'm already thinking about these things, man. So let's say I have 323, it's my number, 323. Okay. I'm going to go from 0 to the length divided by 2. So the length is 3, divided by 2 is 1.5. But we're doing integer division. So it'll cleave off the point, it'll be like, see ya. Okay, so we'll be left with 1. So it'll go from 0 to 1, non-inclusive. So basically it'll just start at the first guy, or the 0 index. It'll start at the 0 index and compare him to the last guy. If that checks out, it's done, right? Because the middle guy, we don't need to compare him with anybody. It doesn't matter what he is. If the other guys are the same, it's still a palindrome, right? Like 323 is a palindrome, despite it being odd. 2 is 2. It's the pivot point that everything's going around, right? And so if we're looking at our code now, it handles it already. Great. I didn't plan this ahead of time. You just gotta think. Sometimes if you're like, how should I handle this? Well, maybe you can get some ideas by looking at how your code handles it already. All right. Cool beans. All right. If strnum x is equal to strnum len strnum. Bear with me here. I see what we're doing. All right. So if I we're gonna say does not equals. If it doesn't equal, so basically I'm gonna explain more in detail about what that test does in a second. But it basically just know it tests if it's a palindrome, or if they're equal, if the numbers are equal to each other, by just testing if their string versions are equal to each other. So if they're not, though, first I'm going to say palindrome, hope I spelled that right, is equal to false, I'm going to break out. No need to test anymore. If one of them's not a palindrome, we're good. Then I'll say if palindrome, if palindrome, then we're going to append it to nums. Let me see if I discarded it. Okay, nums append num. Okay, and then when we're all done testing everything, we'll give us the max of nums. Alright, that's what I'm thinking. Okay. So what am I doing here? Whoa, what's this? -1 minus x? What the hell? So if I go strings num x, so let's just plug in, let's just go through an example. 323. Okay? So all we need to do is compare the first guy. Okay, we're just index 0, okay? So if index 0 is equal to, well, we want to compare him to the last guy, right? And it's of length 3, but we start counting at 0 for indexes. So that means the last guy is at index 2, right? Okay, so we're going to start the last guy by going len string num3 minus 1, because we start at 0 counting, to minus x, right? Because say we were testing the next guy, right? We want to test the guy second from the last, right? If we had the original 4224, right? So if, I'll test the second guy, or 1, and then I'll test this right here gives you the last guy minus x, which would have been 1. So the last guy minus 1. Okay. Okay. I didn't plan this at a time. That's what someone just saw, right? So this is a solution that's coming to mind, right? You may have come up with another solution, okay, ahead of time. Okay. This is good. Yeah. If palindrome nums, let me see if I spelled palindrome the same everywhere. Oh no. Alright, so determining that as a float, so the len is obviously returned as a float. I had no idea. I had no idea that was the case. So you learn something new every day when you experiment. I don't need that there. I can just put that there. Perfect. Well, that didn't work. That's funny. That's funny. Alright, so we can put it in a debug. Maybe I won't pause the debug. So let's print strnum. I don't want a thousand, so I'm just gonna say if x equals 100, print strnum. Just gonna put that in there so we get one thing just to see if it comes out right. Okay. Makes sense. 100 times 100 should be that. Okay. So palindrome equals true. If there's something that doesn't work, break out of it. Alright, for this final debugging, I don't think I'll unpause it. Unless it starts taking too long, so you can see how I'm thinking. Alright, let's think of some errors here. Alright, let's walk through it. So num equals x times y. We're going to automatically assume it's palindrome. Boom. As one thing, let's just print out nums first off, just to see what it gives us. It's doing its thing. It's taking a while this time. Huh. Wonder what that jazz is about. Let's just print out the first one. Maybe it's taking too long to print out the array. Zero, huh? It's appending 0, which isn't good. Num is equal to x times y. Palindrome equals true. Got it. Make a string out of it. Got it. That's just our test. For x, I should probably call that z. See if that did it. Oh no. Well, I'm pretty sure the index should... Oh, hey, look at that. Oh, minus x. Minus x, look at that. We have x up here. It's not good. We were putting in x, so I think it was thinking this big guy up here. This is the daily life of the program. Oh, look at that. Now let's print out real numbers. Alright, here we go. Test. I think we're gonna get it. I think we're gonna get it, boys. Get hype. Oh, dude, by the way, my twin brother played his first competitive video game match yesterday for Overwatch. He's representing his college. They won, dude. They destroyed 2-0. Oh, we did it! Woo! Oh, boy. Oh, I don't know. It's 54 minutes into the video, dog. We did it. Yes. Get hype. Oh, hey, look. The previous parts of this video are still being edited. Dude, that's like Inception of videos. Oh, boy. Okay. All right. Sounds good. So that should give you an idea. I have a test later today. Look at me not studying. It's in 5 hours. I'll be okay. So that should give you an idea of the thought process of doing basic problems like that. Because a lot of the problems that you face, for example, I do swarm-based robotics. Holy crap, that is a complex topic. I'm not even going to be as bad, it's not that hard. No, overall, to understand, there comes a point where you can't even fully understand what something you may have created line by line does as a whole anymore. What? You know, like you just can't remember the scope of what you've done. And man, does that get hard to update code sometimes. But everything you do can be broken down into tiny problems that may not necessarily be this easy, but a lot of the time they can be. If you go through my tutorial series for building that cloud server, a lot of the problems we face, building a file transfer thing, like right now I haven't put up the next video for images, procrastinating, woo! But a lot of the videos, we say, okay, our goal is to get it to transfer files and handle errors and read bytecode, together, that's a complex thing. Each video is 40 minutes. But you could break the task up into tinier pieces. Like we broke sending a file into just, I'm just going to read the file into bits. And we just said, I'm just going to read a chunk, 1024 bytes at a time. And that was just a simple for loop. And we're just going to append it to like a thing, right? Then when we're done, we just do one function that turns it into bytes by just going through it. And then we just send it a byte at a time, right? It was just 3 little easy problems broken out. That took a really big, complicated sounding thing and broke it down. So, and just like we did with things, we said, we need to do 2 loops. And we made 2 loops, right? We haven't solved the problem. We haven't come close, right? We don't even know what we're going to do for the future. We had no idea at the beginning we were going to do this. But we crossed that bridge when we came to it by just breaking up what we were doing a little bit at a time. Okay? I don't want to spoil any more Project Euler problems for you. I hope you feel more confident in your ability to reason through programming problems. And I'll see you guys next time, alright? Peace.